So hi everyone, welcome to Big Data Champs, and this is the session number 4 of our Big Data series. And in this session, I'll be covering the HDFS architecture. Like it is one of the core component of Hadoop ecosystem. I have already covered the Hadoop ecosystem. I gave you an overview in my earlier session, like in the session number 3, session number 2 or 3, I guess. You can watch those sessions first. If you want to want to get a high level overview of what is actually Hadoop and why we need. So till now what we have discussed is basically so let me increase the font size. We have discussed basically what is big data, and I gave you like the formal definition of big data. What is big data? We have understood the different type of systems, be it traditional or we have discussed the distributed systems as well. Then we discussed the Hadoop core component, Hadoop ecosystem and its core components. We have discussed the Hadoop core components. What are the components? HDFS, MapReduce, and the yarn. I gave you the high level overview. Why we basically what are the what is the work these components are doing in the Hadoop ecosystem, and why basically we have to use these components. I gave you a high level overview in my earlier session. And what we have discussed is then we discussed the challenges. We discussed the challenges. We discussed the challenges with MapReduce. Then uh, we discussed on-prem versus cloud. We discussed different type of cloud, different types of cloud. So we have covered a lot. I gave you a high level overview of these things, and till now you must have the clear understanding of these topics that I am like expecting. And now so let's start with the HDFS architecture. So so we know if we need distributed system, and if we want to build an big data application, and we understood like why we need big distributed system. We understood that in our earlier session. You can watch that if you haven't watched yet. So if we have the distributed system, so that these like what is distributed system? Distributed system. What is a distributed system? Distributed system is like a collection, a group of machines, a group of machines or a cluster of machines, whatever you say. And in those machine, one machine will be one machine will work as master node, or master machine, you can say master, and the other machines will work as slaves. So one machine will work as a master, and the another machines will work as a slaves, or the followers of that particular master machine. And this master machine will command these slave machines. So so basically if you want to do some processing, you want to do anything, so that particular request first go to the this master machine, and this master machine will basically forward that particular request to the slave machines to do the actual work. So it is like a manager. It is like a top level manager that is commanding the slaves to do the required work. So that we know. So a distributed system is nothing but a physical thing. But we need, these are some machines. Distributed system is like a group of machines, but we need some framework, some program that will be running on these machines, basically, which will help us to store our data, process our data, manage our data, and that is covered under that we covered in the Hadoop provide these components. What are the HDFS? We have MapReduce, we have yarn. ठीक है. And HDFS basically help us to store and manages the data on distributed system. That we understood. Hadoop, what it does is basically help us to process this data, and yarn is to manage the processing. That these things we will cover in later. First, let's focus on the HDFS because that is the main focus of this session. Okay, so if we want to set up HDFS, so we need to set up HDFS on the distributed system. Then only we will be able to store and manage the data on our distributed system. Okay, that we know. So basically HDFS is again comprises of two processes. So when we set up HDFS on the distributed system, there will be two processes that will be running on our distributed system. So what are those processes? First is the NameNode process, and the second is the DataNode process. It is nothing but like a program that is running a file of code, or bunch of files of code that are running, that has some logic written for the data NameNode process, and what that particular program is doing, that I'll explain in a moment. So NameNode, we have this we have the NameNode, and what does NameNode do? It basically before what it do, we will understand where this NameNode process will run. So it basically runs on the master node. It basically runs on the master node. So it runs on the master node, and that master node is also known as we can call that master node as a primary NameNode, where the NameNode process is running. And then we have the DataNode process. So the DataNode process basically runs on the slaves nodes or machines. And these machines again we can call these machines as like data nodes. Wherever the data node process is running, we call those that those machines as a data nodes. So what is the work of data node? What is the work of NameNode process? Let's understand that thing. So the NameNode is basically stores. It's basically stores the metadata. What metadata? I'll explain. And what does DataNode do? Basically it store the actual data. So what do I mean? If I show you an example, so this is the distributed system, this is the master node, and these are the slave nodes. On the master node, I said like there in the master node the NameNode process will be running, and this process will basically help us to manage store the metadata. And the on the slaves node there will be data node process will be running, and these data node process will help us to store the actual data on this machine slave node. And so if you have, let's say, a customer.csv file, and if you basically want to store the data, that particular file on the HDFS, you will send a request, like write request to your HDFS, like store this particular file. That particular request will go to the primary name node. What it will do, it will create some directories on these data nodes wherever possible, or where it will be more optimized, and that particular file will be stored, that file you have requested, that file will be stored on one of these data nodes. And wherever the file will be stored, let's suppose on the data node 4, if your file is stored on the data node 4, that particular location, the directory name, the directory structure, file name, and the name of the data node will be stored as a metadata in the primary name node. So primary name node knows what data is kept on which data node, what is kept where. So it stores the metadata. Metadata is nothing about the data about the data. It is data about the actual data, or I would say the information about the actual data. So it store the metadata about like what kind of what is what data is stored on which particular machine. It knows uh, what is kept where, in the normal layman terms I would say. So it knows what is kept where. Okay, so it is basically what is the actual work, I would say. So it helps us to basically manage and track the directories uh, or files present on the data nodes, because data node is storing the actual data and name node is storing the like what in which directory or file this actual data is stored, that is stored as a metadata inside the primary name node. For example, if you have a book, so book, what basically a book contains a index page, and then we have the main pages, main actual main chapters I would say. Then we have the chapters, multiple chapters. So index page has the information like on like which chapter is present on which page number. It has a mapping of the chapter to page number. Similarly, so if you go to the index, you will know like chapter number 4 or 5, and like n chapter is present on like which page number. You will directly go to there instead of jumping here and there or searching on the random pages. You will just go to the index page, and you will check which chapter is present on which page number. Name node similarly in HDFS Similarly, in HDFS, we have NameNode, which has the mapping. What mapping? The data, the actual uh, data with data node, actual data location. So the data location, you would say, which data and its location is mapped to which data node, which data is basically mapped to which data node. Let's suppose for example, you have a customer.csv. So it will map it with some data node, let's say data node 2. So what does it mean? If you store a CSV file, and if that particular CSV file is stored on the data node 4, then there will be entry created as a metadata in primary name node, like this CSV file is stored on the data node 2. This is the metadata that the name node is basically storing. So this is the metadata that I'm talking about, that basically name node help us to store. That is okay, but it is helping us, but where it is actually stored in the name node. So there is a file called fs image. These are some terms that will be asked in the interview for sure. So fs image, it is file stored on the name node, and it basically contains the directory structure of the data that is stored inside HDFS, or stored inside HDFS, or you can say the data nodes, because actual data is stored in the data nodes. So it has the files, the fs image file is basically having all the information about like the directory structure, like in which directory a particular data file is stored, on which particular data node. It has that mapping, and that mapping is basically present. The mapping I was explaining you, this mapping is basically present inside this fs image. file, and the NameNode is basically managing this. NameNode process is basically managing this file, SFS image file. And there is another term which is edit logs, So what does edit log does? What is it? So it is edit log is a transactions log file. It basically keep it basically stores the logs of transactions happening. For what kind of transactions? Like addition of new data files, or deletion of files, or updates, etc. So these are some transactions that will be happening. Like there will be new files that are basically we will be adding in the HDFS. There will be files that will be deleting from the HDFS or updating from the HDFS. So those transactions as a log will be stored will be kept inside the edit logs, what are the changes that are happening to our HDFS in the data. So those transactions, if a particular CSV file, I said, like, you have this particular CSV file, and if you deleted, let's suppose first you created this file, let's suppose, so there will be one transaction that will be created inside the edit log, like you create hyphen customer CSV file and uski location and the data node name. Then if you delete this customer CSV file, then another transaction will be created inside the edit log, like this particular CSV file deleted from this location and from this data node. So this is, like, I am trying to give in a high level example how this information is stored, how the edit log is basically managing or tracking the changes. So it is tracking the edits that are happening. So this is how these terminologies, like these terms are important. If I'm talking about with the respective like interview, these things will be asked for sure. Then the data nodes are basically storing the actual data. Data node processes are running on the if you see, these are the slave nodes, and in these slave nodes the data node processes are running, and these data node processes are basically helping us to store the actual data, and the actual data is stored on the data node where the data node process is running. So now I have given you an example. Don't try to focus on the stack in NameNode. What is this thing? I'll explain in a couple of minutes. Just bear with me. So we understood this architecture, what is happening here. So if you storing anything, so that will be first go to your primary NameNode process, and this NameNode process will decide on which particular data node that your data will be stored, and then your data will be stored on one of the data node, and the location of your data, the directory name, the file name, folder name, data node name itself will be again stored and mapped in your primary name node. Like your customer.csv is stored on data node 1 on some folder name that will be there. For example, this one I explained you. So now understand, like how basically the data is stored on HDFS. So let now understand how data is stored in HDFS. Because HDFS is basically set up on, like, we are using HDFS on distributed system, so data has to be stored as a distributed manner, it will not be stored as a single file. Okay, so it is not like if you have 100 GB file and you store on the HDFS, then 100 GB file will directly go to one of the data node. It will not be like that. It has to, if we are using distributed data storage, then the data has to be stored in a distributed fashion only. What does it mean? Let me explain. Let me explain how data is stored or how HDFS store the data. So if you store a file, let's say 1 GB file, or let's say 10 GB file. If you store a file on HDFS, then what will happen? First, HDFS will, divide that file into smaller chunks, and these chunks are basically we call blocks. That if you store a file, then HDFS will divide that file into blocks, and the size of each block will be the size of the blocks. The blocks will be 128 MB. This is the default size. You can change it if required, and like this is the standard size that is basically we use. So we have the 128 MB size block that will be created. If you store a bigger file, that will be divided into smaller chunks, and these chunks we basically refer as a blocks. And then these blocks of data will be stored on the data nodes. This will be stored on the data nodes. So that we have discussed. Your data node storing the actual data, and your name node is storing just the metadata. So if you store if you store a 10 GB file, so first that file will be divided into blocks of 128 MB each block size, and then these blocks will be stored on the data nodes. So suppose if you have, let's say, one in 1 GB, how many blocks will be there? We will be having, let's say, 8 blocks. We'll be having 8 blocks. If one block is 128 MB, then we will be having 8 blocks. We'll be having 8 blocks. So in 10 GB, how many blocks we'll be having? We'll be having 80 blocks. So these 80 blocks will be distributed across these data nodes. So these data nodes will be having these 80 blocks stored in a distributed manner. So let's suppose if we have 4 data nodes, then 20 blocks will be stored on the different data nodes. 20 data node 1 will be having 20, data node 2 will be having 20, data node similar fashion, the 20 data blocks will be stored on the different data nodes. Let me explain you this thing with an diagram example. So suppose you have a file, you have a customer file, customer.csv file. For example, you have a customer.csv file, and the size is, let's suppose, 600 MB, and the block size is, we are considering block size of 128 MB. So if you store the this file on HDFS, if you store the file on HDFS, then how many blocks will be created? We will be having five blocks. We will be having 5 blocks. So the first 4 blocks 128 MB. First 4 block will be having 128 MB, and the last block will be 128. This will add up to 512, and the remaining 88 MB 88 MB will be the 5th block. So this is block 1, this is block 2 size, then we have a block 3, then we have a block 4, okay, and the 5th block 5. So we have these different blocks, and these blocks are basically created from this customer CSV file. Okay, so you have this file stored on your HDFS, and so basically the five blocks are basically, it is divided into five blocks, and the five blocks, these five blocks actual data will be stored on the data nodes. We have discussed that the data nodes will be storing the actual data, so these blocks, the actual files, smaller files, will be stored on the data nodes. So let's suppose data node storing, like, has stored this block 1 date, similarly data node 2 has the block 2 and block 5, and similar data node 4 has the block 4 stored on it. Let's suppose uh, uh, some home directory data, uh, data node, some customer. I'm just trying to give an example. Customer data, block 1 dot csv. This has a size of 128 MB, and data node, so it will be stored on data node on this location, for example, and this is the size of the data, the file. This is the size of the data file. So this is stored on the data node, let's say 1. So similarly, your block 2, block 3, block 5 will be stored on the other data nodes, and so this information about this block and about the data node on which this data is stored, this mapping is basically stored as a metadata. This mapping is stored as a metadata inside the primary name node. You can see this has created a metadata table, and it is storing this, a mapping. This particular block file, block 1 file, is stored on data node 1. This block 2 file is stored on data node 2, and again it has mapped what is the main file, basically, which these blocks belongs to. So the customer CSV is the main file that we have stored on the HDFS, and HDFS has divided that file into 5 blocks, and it has created a mapping between these blocks and where these blocks are stored on the data nodes. It has created a mapping, and this mapping is stored inside the metadata table, and primary name node is basically responsible for maintaining this metadata table. Okay, so we have understood how the data is stored, and if you basically run a query, suppose HDFS cat command, basically, which is used to read the content of a file, and so if you read, if you write this command, execute this command, it will request it. This request will go to the primary name node. The primary name node will check its metadata where this file is stored. It will check, okay, CSV file is basically has mapping with these blocks files. It will check, okay, these are the data nodes on which these files are present. Then it will further command send this command to these data nodes where the files are stored. These commands will run on these data nodes, and these data nodes will send the result back to primary name node, and this result will be sent back to you. If you see, this is the result that you got. Let's suppose customer ID, name, and gender. This is the result that you received from the primary name node. So this is the whole process, how basically the data is divided, mapped, and stored in the HDFS. I try to give you an high level overview, that too in the very layman terms. So let's move ahead and see. So till now I have covered about, like, the primary name node, data nodes, how the data is basically stored and maintained and managed basically by the HDFS. But if you see, like, the our main point of contact, our main point of contact to interact is primary name node. Our main point of contact is primary name node, and what I mean by that, whenever you are running some query or like commands, it will be sent to the primary name node. It will be processed by the primary name node, and primary name node will be fetching the data from that is stored on the data nodes, and it will send back to you whatever be the result. If if this master node basically fail, in it at the end it is a machine and it can fail. If this fail, then what will happen? If primary name node fail, then what will happen? who will be who will take who will take over, or how basically the operations will be managed if this particular thing is failed. Because if there is if we do not have anything for backup, then it will lead to a SPOF, another term, single point of failure. It will lead to a single point of failure if there is not anything, like if there is not any other machine who will work as a backup for the master node. If there is nothing like that, then this will be a single point of failure, and if the master node fail, our entire cluster will go down and we will not be do anything. Our HDFS will be basically will be down, and we will not be able to use that. So if the primary name node fails, so we have a secondary name nodes concept. So there will be secondary name nodes, multiple secondary name nodes, basically multiple machines. And if basically name node, primary name node, there is, if there is any failure in the primary name node or so the master node, this master node, then this secondary name node will come into the picture. It will take over the primary name node. So the secondary name node will take over the primary name node in case of failure. In case of failure, the secondary name node will come into the picture and take over the primary name node. The secondary name node works as a standby nodes. Basically, they are there as a backup. They are there as a backup. So if primary name node goes down, then secondary name node will take over the primary name node. But now you will ask another question. Okay, Saurabh, like the secondary name node will take over, but we discussed like this primary name node has something called FS image, edit logs. How these things are basically transferred to the secondary name node? If if this particular name node, primary name node goes down, then this we will need the FS image and edit logs. Then only our HDFS will be able to manage the things, or the data that is stored on the data nodes. Then how our secondary name node, these secondary name nodes will get the this metadata thing. How this metadata will be transferred to the secondary name node, then only it will be able to take over the primary name node, because we require this metadata in which all the mapping has done. So then the concept comes, another concept comes, checkpointing. Okay, these are some important terms, concept that you will be encountering in your interviews for sure. And what is checkpointing basically means, so if your as I just said, like your secondary name node will take over the primary name node if the master node fails, but this primary name node was able to fulfill our request or manage the data, because it has the metadata table in which all the logs are stored, like which data block is stored on which data node. But this metadata has to be transferred to the secondary name node, because if it fails, if the master node fails, then there will not be any way to transfer this metadata to the secondary name node. So we have to keep updating this metadata, or we have to keep sync we have to keep in sync the secondary name node with the primary name node when the cluster was up. Basically, if when the cluster is healthy, the name node is up, then in like that time only we have to keep the secondary name node in sync with the primary name node to basically send this metadata to this secondary name node. So in case of failure, in case of any failure to the master node, secondary name node will have the ability, will have the metadata with it, and it will take over the master node. But now the thing is how this sync operation is happening, like how the updated fs image. So this metadata table is nothing but fs image. Metadata table is nothing but the fs image that I have already talked, discussed about. So what was fs image? Fs image basically is the file that is stored on, that is present on the name node, primary name node, and it contains the directory structure of the data stored on the HDFS data nodes. So in this file, we have all the information which data block is stored on which directory or which folder, and this fs image has to be transferred, shared, has to be shared or with the secondary name node. And basically these two name nodes has to be in sync. Then only in case of failure, our secondary name node will take over the master node. Because if secondary name node doesn't have any information about the metadata, it won't be able to take over the primary name node, because we need metadata. So the checkpointing, what happens, it is a process of merging the old fs image and edit logs. So that an updated fs image will be created, and this updated fs image will be basically shared between, it will be present in both, it has to be present on both the name nodes. Then only the failure of master node can be handled by the secondary name node. So let me explain. If you see here, so on primary name node, if you see, we have the some initial base fs image, some initial directory structure, what is the blocks are stored on the different data nodes. We have some initial changes. So what will happen, a user come and a user made some changes. Okay, let's suppose he created, like a user has created, let's suppose, a new file or deleted new file. So some transactions or will be created inside the edit logs, that I have already explained what edit logs do. Edit logs basically maintain all the logs, what all the changes that are happening to our direct to our data. So user has made some change, and those transactions will be captured inside the edit logs. Then what will happen, these edit logs will be transferred to the secondary name node. So secondary name node will again will get this edit logs, and the secondary name node has already copied the initial fs image. The secondary name node has already copied the initial fs image, the base fs image. Now what will do, whenever, as soon as it gets the edit logs, it will merge the edit logs with the fs image, the base fs image, the old fs image, and it will create a new fs image, the updated fs image, the fs image checkpoint. This is the new updated fs image, and then it will send this fs image back to the your primary name node. Now your primary name node has the new updated fs image. So if a new request come, this primary name node will use this fs image, and now this fs image, updated fs image, is present on the primary name node as well as the on the secondary name node also. So your secondary name node also has this updated fs image, and your primary name node also has this latest fs image. So now if your primary name node goes down, or there is any failure in the master node, this secondary name node has this updated fs image. It will use this fs image, and it will take over the primary name node in case of failure. That's how this checkpointing process is happening. So checkpointing, what is checkpointing? Checkpointing is nothing but merging the base fs image with the new edit logs, with the new transactions, so that we will get a new fs image, basically new fs image, and this FS image basically will be transferred to the primary name node, and primary name node will use this FS image or this metadata to basically help us manage the data that is stored on the data nodes. So this FS image is nothing but this metadata only. The FS image has this data, this metadata table. This is nothing different. So this is how secondary name node is helping us to do the checkpointing, and if the checkpointing we are able to get the updated FS image, and this FS image is basically used further sent to the primary name node, and your new request will be resolved using this FS image only, the latest FS image, because there will be new changes that will keep happening, like new data files that will be you will be getting from the data sources, and you will be storing your HDFS. So you should have the updated FS image, updated metadata, and for update to create the update, to basically continuously create updated metadata or updated FS image, we have to do the checkpointing process, and this checkpointing process is something that I have explained how it is happening, and secondary name node is helping us basically to do the checkpointing and to basically maintain a updated FS image. Okay, so this is the checkpointing. So how the secondary name node basically helping us is in the two way, I would say. So secondary name node helping us in two ways. What are the ways? Let me explain. So the first is it helps in checkpointing. What is checkpointing? Keep updating the FS image. Keep updating. It will keep updating the FS image using the edit logs. Okay. And the another way it is helping us is, so in case of failure, it will take over the primary name node. It will take over primary name node in case of failure. Okay. So if our primary name node fails, then secondary name node will take over, and it will basically resolve all the requests that are coming to the primary name node. So it will basically work as primary name node in case of failure of primary name node. So we understood how the secondary name node was basically is helping us in which scenarios. So now if I show you this picture, let's say this one, and if you see, like, we have multiple data nodes, and basically these data nodes carrying our actual data, and basically our actual data is stored on these data nodes. Primary name node was just holding our metadata table or the FS image. So in case of primary name node, the secondary name node was there to basically take over in case of failure of primary name node. But what if I tell you, like, what if the data node fails it? So the data node has your actual data, and what will happen if your data node fail? Because at the end it is a machine and it will fail, it can fail. So how will HDFS will take care of the scenario? Does we have any fault tolerance thing in that basically HDFS provides us fault tolerance or not? Yes, it does provide. And how? Let me explain how HDFS provides us fault tolerance. Fault tolerance in HDFS. So basically HDFS maintains 3 replicas or copies of each block. It maintains 3 copy or replicas of each block on different data nodes. For example, For example, you have, let's say, your block 1, block 2, block 5 on the different data nodes. What it will do, it will create the two more copy of block 1. Let's say this was the original block. It will create block 2, another copy, block like third copy also on the data node 3. So there will be total 3 replicas, including the base one, the original one. So it just created 3 copies and distributed across the different data nodes. So in case of failure of data node 1, and so if the data node 1 basically fail, then we still able to read the block 1 from the data node 2, because we have maintained our replica on the another different data nodes. So we have maintained our copies on the different data nodes. This is how HDFS provide us fault tolerance. But how these replicas are stored on data nodes? So basically HDFS store replicas on 2 different racks. Now what does rack mean? Rack is nothing but a group of machines on data center. For example, let's say this one. So we have this data center, and we can see like these are the rows. Racks. This is one rack, this is another rack. Similarly, we have multiple racks, and in a rack we have these multiple machines. In a rack we have multiple machine, another rack we have multiple machine. Similarly, there are multiple racks as well. So what the HDFS will do, if you have, let's say, block 1, so block 1 will be stored on, let's say, on the top first machine. Then what will it will do, the second and third replica of a block will be stored on the different rack. The second and third replica will be stored on the different rack. Let's suppose this is the second rack. So your second replica will be stored on, let's say, this machine. The third replica will be stored on the same rack but on the different machine. So you have to store 3 replicas, 3 copies of a block. So what we'll do is HDFS will do, first copy will be stored on one of the machine on the rack 1. Then the second and third copy will be stored on the second rack itself, but on the different machines. So HDFS basically stores the replica on 2 different racks. Okay, so your first replica stored will be stored on on data node, or say machine on rack 1. Second and third replica, I would say, second and third replica will be stored on the rack 2, but on different I would say machines, but on different machines. So the first replica is stored on the on one of the data nodes or machine on the rack 1, but the second and third replica will be stored on the rack 2 but on the different machines or nodes. So this is how 3 replica of each block will be created. If you see, first replica of block 3 is stored on the data node 1, the second replica is stored on the data node 2, and the third replica is stored on the data node 4. Similarly, we have the block 5. If you see, block 5, first replica is stored on the data node 1, the second replica is stored on the data node 3. You see, block 5. The third replica is stored on the data node 4, block 5, you can see. So for every block we have 3 replicas stored, and that's how the HDFS provide us fault tolerance. So in case of node 2 fails, we have all the replicas present on the different nodes, and we will use those replica from those nodes. Okay, so there will not be any issue, and that's how HDFS provide us fault tolerance. So we have understood, okay, like if the data node fails, then how SDF is providing us the fault tolerance thing. Okay, but the next question that I would ask you, like how NameNode will get to know that the data node has failed. How will get to how the name node will get to know, how the primary name node will get to know if the you know if a particular data node has failed or not. So then only then only name node will be able to transfer the request to the another data node where the another replica is stored. If the primary name node itself don't know if the data node 1 has failed or not, then it will keep sending the request to data node 1. There has to be some mechanism that the primary name node will get to know, okay, the data node 1 has failed, so I'll transfer the request for the block 1 to the another data node where the block 1 is stored. That should be the flow. So how the name node will get to know is basically the data node sends heartbeats signal to primary name node every 3 seconds. So it will keep sending heartbeat signal to primary name node every 3 seconds, and if the primary name node does not receive any signal for you say signal for 10 consecutive time, or I would say 30 seconds, then primary name node will assume that the data node that the particular data node has failed. So this is how the primary name node will get to know, okay, the data node has failed. That is also something that I wanted to explain. The another thing now I want to explain is how is basically the size of a block is decided. I explain we are taking the block size 128 MB. How we decided why this is 128 MB only? It can be 64, it can be 250, 512 MB, 512 MB, it can be 1 GB. How, why we are using only 128 MB? Let discuss that as well. So suppose what if I'll take the two scenarios. Case 1, if we have block size greater than 128 MB, what will happen? Suppose for example we have, let's say we have 100 TB file, and how many blocks will be there? So for example, for 1 GB file we have 8 blocks. Considering the block size 128 MB, we will be having 8 blocks for 1 GB. Then 1 TB, how many blocks will be having? Because 1 TB we have 1000 GB, then we will be having 8,000 blocks. 8,000 blocks. And in 100 TB file, how many blocks will be having? 8 lakhs blocks. 8 lakhs. These are the number of blocks that we will be having, and these blocks will be stored on data nodes, and their metadata will be stored on NameNode. that we know, that we have already discussed. The metadata will be stored on primary name node, and the actual data will be stored across the multiple data nodes. But there will be only primary single name node that will be handling all the metadata. So this primary name node will be handling single-handedly like all the metadata, but the actual data will be distributed across multiple, stored on multiple data nodes, and metadata will be stored on single primary name node. So now let's see, if we have 128 MB block size, how many blocks we are getting 8 lakh. We are getting 8 lakh blocks. What if let's say let me decrease the size first. So we are considering case 1, if we have a block size less than 128 MB. So let's suppose I'll take 128 MB block size. How many blocks I'll be having? It will be 16 lakhs. And if I divide it further, let's say if I decrease my block size to let's say 32 MB, how many I'll be having? 32 lakhs. So if you see, as we are decreasing the size of block, the number of blocks is increasing. Since we will be having, let's say let's say we have multiple data nodes, so our actual data will be handled somehow, where actual data will be stored. So on the multiple data nodes, somehow these blocks will be stored, because we can increase the number of data nodes, that we know. But the thing is, we have only one name node. So if we decrease the size, then what will happen? The number of blocks will increase. Indirectly or directly, the metadata, the size will also become huge. And if the metadata size is become huge, then what will happen? The huge metadata will be basically will be stored on the name node, and will overburden the name node, because we are having like lots of metadata on the name node. So if we have, let's say, if we decrease the size of the block, the number of blocks will be increased, the number of directories, number of files. What is metadata? Metadata is nothing but the files, the data about the files and the directories, data about the actual files and directories. So this will increase a lot if we decrease the block size. So we will be having a lot of metadata, and if we having a lot of metadata, then what will happen? This lot of metadata will be stored on the single name node, and it will overburden our name node, and it will lead to decrease in performance. Because if you have, let's say, if you if you run HDFS, let's say, what is PDFS? HDFS DFS-cat. If you search this and you say customer.csv, what will happen? Suppose this is like if NameNode has a huge amount of metadata, and if you just want to search for this particular file, want to see the content of this file, then NameNode has to search through a lot of metadata to get this file location where the blocks of this file is stored. You are getting my point? Scanning huge metadata will be time consuming, and it will decrease the performance. it will decrease the performance. So this is why we should not decrease the block size, and we should maintain the block size as a 128 MB. Now you will say, okay Saurabh, we will not decrease the block size, but what if we increase the block size? Okay, let's see case 2. Case 2, if we have block size greater than 128 MB, then what will be the case? Let's say we have a file of, let's say, 2 GB file. Let's say we have a 2 GB file, and if we have 2 GB file, how many blocks will be there? Blocks will be there 16 blocks. Okay. So 128 MB, we have 16 blocks. Then if we take 64, sorry, we have to increase the size. So let's say 256 MB, it will become 8 blocks. Let's say 512 MB, it will become 4 blocks. So what is happening here? As you increase the size of the block, we are having the less number of blocks, and if we have the less number of blocks, then we are basically not utilizing our parallel processing. For example, suppose we have 5 data nodes available. And we only have 4 blocks to process. Then what will happen? Out of these 5 nodes, we will be using only 4 nodes to process these 4 blocks. Okay, and we are not utilizing our available all the data nodes, and we would have if we would have used all the data nodes, our data might have processed in a bit less time, because the processing is being done parallelly. If we instead of processing, let's say 20 MB 5 files on the 20 MB 4 files on the 4 nodes, if we process 15 MB 5 files on the 5 nodes, it will be very time efficient. The job will complete in a lesser time. So that's how we are basically what we are losing here is we are not utilizing the parallelism efficiently. We are not utilizing the parallelism efficiently. Okay, if we are decreasing the basically if we are increasing the block size, the number of blocks will be less, and we are not basically utilizing our available data nodes, if there are any. And otherwise we would have basically, if we would have utilized all the data nodes and to basically process all the data, then our job might have completed in very less time. If there are less number of blocks, then basically we are not utilizing the parallelism up to the mark or efficiently. So this is the case. But so this is why basically we should keep our block size as a 128 MB. This is why we should keep our 128 the block size as 128 MB. This is the standard one, that is we should use. Okay, so this is what I wanted to explain, and we covered a lot actually in this session. So we have covered a lot in this session, and I hope you guys have understood most of the things. And if you have any questions, any doubt, you can please comment in the comment section, and we'll try to revert back to you for sure. So that's it for this session, and we will meet in the next session.